So for today's session, it uh, it will still be me. I'm the substitute teacher. So basically, we're gonna cover from encoder decoder. If you haven't finished reading last time, all the way to right before attention is all you need, or transformer. So literally at the end of 553, page 553. So page 542 to page 553.
And you are the co-host, Wenchang, not the substitute teacher.
I was just joking. Yeah, so basically, yeah, so next session, Wednesday, will either be me or Gotham, then we'll finish Transformer. So yeah. Okay, so and we'll spend 45 minutes on the reading. So we'll regroup at 2 p.m. EST, and or should be 11 a.m. PST. Okay. Time is up. How's everyone doing?
Pretty good. Yeah, great.
Cool. Cool. Um, great. So I assume you guys all finished reading. It's actually probably a lot to read in 45 minutes. And the next session will be probably even more so. There's just, I mean, it's just extremely hard for anyone to understand all these networks within 45 minutes without, spending extra time and efforts digging into it and reading the paper or other supplementary materials. Okay, so encoder decoder neural network. And let me just start sharing the screen. Okay. Basically, it's I mean, the name is pretty self-explanatory. This neural network has two parts. One is encoder, one is decoder. And in short, basically, the encoder takes in the English sentences, and the decoder outputs the translation. In the case of machine learning, machine translation model. And for example, milk, drink I will go into the encoder parts, and this is the decoder parts. And it will basically output the French translation. I don't know French, but assume that's the French translation. And again, it's by time steps, and every time step is a word, right? And also you would need to do the embedding lookup first, as we kind of explained previously. If you look at what we had previously, it would basically you have embedding layer first, then you go through the time steps. Okay.
Question, Wenchang.
Yeah.
So is it actually common to reverse the input sentence? Because I have not seen that before. The milk drinks, I think. Yeah, milk
Yeah, I
drink.
think he kind of explained it. I remember it was explained somewhere. Yes. I think it's because in if you reverse the order, the decoder will actually output the sentence in the correct order.
Yeah.
That's
I mean, I did read the explanation, but I have not seen this before in any of the previous examples that we have seen. I mean, not in this book, but outside. And like even the explanation that he gives, like if you reverse the input sentence, the distance between milk and the corresponding French milk increases, it doubles, right? So it may not be that good as he claims it to be.
Which one doubles? Sorry, what?
So distance between the English word milk and the French word for milk, you double it basically, because milk is now the first word and it's the last word of the French sentence, right? So it's a compromise. Like, did you understand?
Okay. Yeah, but how does that distance? Can you explain? How
No,
does that distance matter?
the reasoning he gives for reversing the English sentence is the starting of English and the starting of the French are now basically touching, right? So it's easier to start writing your translated sentence.
Mm-hmm.
Whereas, I mean, because if the English sentence were written in the normal way, then the
Mm-hmm.
first sentence of English and the first sentence of French are far apart. So the hidden state might get changed by the time it reaches the decoder. So that's why he
That's true.
reverses it.
Yeah. Mm-hmm.
But while reversing, what happens is the last word of English, which is milk,
Uh-huh.
is now really far from. Uh, I mean, yeah, you. So the last part of the sentence gets affected.
Mm-hmm.
So in a way, you're not. I don't see why this is better.
Does anyone else has anyone else seen different implementations, meaning like not reversing the order of the input sequence?
Yeah, actually, even 2 years back, I mean, the latest 224N was PyTorch based, so they don't show any of this reversal. And my recollection is the TensorFlow version of 224N, the Stanford thing, sequence to sequence, that didn't talk about any reversal either. So don't know whether that's unique to this book and what he's talking about, but I echo what Gautam is saying. At least I know that both 224 ends, the PyTorch version and the TensorFlow version, to my recollection, doesn't do the reversal as he talks about it here.
Okay, and let me see how he reversed the order in the code.
Yeah, just to add, on the
Yeah.
paper, the C2C, they have also, if you open that up on page 4, there's a whole section of reversing the source sentences, and they have proved that in practical scenarios, this helps in uh, getting the predictions for the later part of the translations. So in a sense, what they said is they have trained on the early part of the target sentences and the later part of the target sentences, and they have compared it, and what they have found is this works better.
So you're talking about the source.
Yes, of the source.
Okay. Which one?
Yeah, let me, yeah, give the link to the paper. I think so. It is there.
Is that the number 10? Sequence to
Uh,
sequence learning with neural networks?
yes, number 10.
Okay.
So on page 4, there is a whole paragraph there.
Page 4. Which one?
Page 4.
This
Yeah,
is page 4.
reversing the source sentence. Yeah,
Okay.
3.3.
Great. Yeah, let's read about it. So while the LSTM is capable of solving problems with long-term dependencies, we discovered that LSTM learns much better when the source sentences are reversed and target sentences are not reversed. By doing so, the LSTM's test perplexity dropped from 5.8 to 4.7. The test blue score of its decoded translations increased from 25.9 to 30.6. While we do not have a complete explanation to this phenomenon, we believe that it's caused by the introduction of many short-term dependencies to the data set. Normally, when we concatenate source sentences with a target sentence, each word in the source sentence is far from its corresponding word in the target sentence. As a result, the problem has a large minimal time lag. By reversing the words in the source sentence, the average distance between corresponding word in the source and target is unchanged. So Gotham, I think this corresponds to what you were saying. This is actually unchanged.
The average is unchanged, yes. But for some words is higher and for some other words is smaller.
Sure. However, the first few words in the source language are now very close to the very first few words in the target language. So the problem's minimal time lag is greatly reduced. So it's actually, the first few words are actually closer, right? Because you're reversing the order. Thus, the back propagation has an easier time establishing communication between source sentence and target sentence, which in turn results in substantially improved overall performance. So thank you, Mayank, for this reference. Yeah.
I I have an observation that
Sure.
just spot off my mind. I remember that for searching strings in a text, it is better to start searching for the end of the string than from the start, because for example, if you have well, this is for normal searching of strings. I remember that there was an optimization that if you have a sentence of 5 words, you start searching for the last word, and from that place you go backward to see if it matches your string. So that
Okay.
was one optimization, and I think it is something related to maybe like they say, we don't have an explanation, but thinking of search algorithms, that also one of the optimizations is to look first for the end, even that your target strings and your search string are in order. I think it could be also related to that, maybe. Just saying
Okay.
it because I find the similarity.
Yeah. Yeah. And also, I think for language model or translation, it's probably important to have the first couple words correct, right? As we can see from the Beam search, when you have it's greedy. It's in somewhat it's greedy, right? And if you have the first word correct, then the second word is more likely to be more basically correct in terms of grammatic structure, or it would make more sense. So perhaps you even though on average the distance is unchanged, but you might want to closer distance for the first few words. Gotham?
Yep.
Okay.
Makes sense.
Yeah. So okay. Any questions on this structure? I thought this was relatively straightforward. And at each time step, the decoder outputs a score for each word in the output vocabulary. So in the end, you're basically then softmax that into probabilities. You know, for example, perhaps this word, French words, I don't know how you pronounce that, may have a probability of 20%, and two, where is two? It says do, but here it says two. Maybe it's wrong. But
yeah, so the drink word is bois in French, and dieu is some. Basically, it stands for some, SOME.
okay, so this is drink.
Yeah, BOIS is bois. That stands for drink.
Oh, this is drink. So what about this one?
Means I.
Means I. Okay, I drink. Oh, got it. I drink
some milk.
Some milk. Got it. Okay. Got it. Cool. Thank you. And it has a probability of 1% and so on. The word with the highest probability is the output. So I think it's important to stress that basically, so this is, I believe this is inputted when this should be inputted together. I believe that's what it is.
It's an LSTM, right? So
Yeah.
it's one word at a time.
Oh, one word.
Milk,
Okay.
and then
One word at a
drink,
time.
and then
Okay. It's one word at a time, and each time step is one word.
Yeah.
Yeah. Okay. And then you're outputting one word at a time too, right? And
Yes.
so even though it's presented like it's outputting a whole sentence together, but it's actually each time step. So so again, this is one time step, this is one time step. So we're going through 5 time steps, and this is 3 time steps. And including the end of sentence tag. Okay. So any other questions on this?
So could you scroll back up a little bit for the
Sure.
Wencheng? So you could see the encoder decoder. Yeah. So I'm not sure how this works. The encoder part, that works all at once, right? It generates one output, one hidden state as an output, and then that goes into the decoder part on the right, and then it gets propagated through step by step in 5 steps to produce the output. Is that how folks understand
Yes.
how this thing works? So the embedding lookup on the left is all done at once. It's one step.
But the words are seen sequentially.
Mm-hmm.
The words are
So-
seen sequentially. So, but there's one output, right? There's one hidden state output that goes between, that gets then fed into the decoder.
That's right. So
Correct.
you have a
Yes.
hidden state that gets modified as it sees each new word. So first
Okay.
it sees milk, and then you get a new hidden state. Then it sees the word drink,
I see.
and then it gets a new hidden state. And then the final hidden state is what's given to the decoder.
I see. So the advantage of doing this, of putting the sentence in backwards, is that it now remembers mostly from the first part of the sentence when you go to do the translation of the first word, I guess. Right? Because that hidden state that's being fed into the decoder has memory, and the freshest memory is from the first word in the sentence.
Mm-hmm. Yeah.
Yes.
So, but I've never seen it done this way. I guess I've never seen it done at this fine of a scale, because otherwise I would have noticed this before, that things go in backwards. I don't remember seeing that in any of the other encoder decoder models I've looked at.
What because since some of us went through CS224N from Stanford, and Joseph, you were leading some of the sessions. I forgot who led the encoder decoder session, but was that the case that was shown back then for CS224?
Well, that's what I'm saying. I don't remember things going in backwards. That's maybe we just weren't looking at it at a fine enough scale or fine enough detail.
No, it was not reversed. Like Srinivas
No,
said,
it was
in
not reversed,
CS224.
Joseph. Not
It
in
was not
PyTorch,
reversed.
not in TensorFlow example the year before.
Yeah.
Both years it was shown as being fed in sequence.
And however, I guess the original paper implemented it this way. So yeah. And on the other hand, can someone tell me was there something that's indicating this was reversed in the code? Because I couldn't tell.
I think this is just the model, right? So they don't have the data in this code, or do they?
There is some statement here saying the reverse thing is true. If you look at the code that you have put up, the box before this,
Yeah.
return state equals true. Does that have anything to do with it?
No, return state it just means you're returning the state on every step. I think.
Yeah.
Okay.
Hidden state.
Exactly what he explains in the book.
Yeah, and yeah, maybe it has to do with this one.
Venjak,
I
how
don't
does he
know.
build encoder inputs? He has something called encoder inputs.
Encoder inputs right here, and just feeds into the encoder embedding. Yeah, I don't see.
He has not shown a proper example with text, right? It's just numbers, I
No,
think.
no,
Yeah,
yeah,
that's why.
that's what I'm saying. Yeah, and yeah, it's just numbers, bunch of numbers.
The reversing would come in the data step, right? Not in the model. So he would just reverse the strings before inputting to the model. Yeah.
Yeah, yeah. Maybe it's this. This looks like it's a reverse, but I'm not sure if I'm not 100% sure. And yeah, he unfortunately he didn't even show the example as text. It's unfortunate. Okay, well, let's go through the code. So again, he has encoder inputs as char.layers.inputs, not specifying the shape. D-type numpy integer 32 decoder inputs, same thing. Sequence lengths, right here as char.layers.inputs. Vocabulary size of 100, embedding size of 10. Then he calls on embeddings as char.layers.embedding vocabulary size, embedding size, encoder embeddings equals to embeddings encoder inputs. So that feeds into this. Decoder embeddings equals to embeddings decoder inputs. So that goes to here. Encoder equals to char.layers LSTM 512 units, return state equals to true. Encoder outputs state H, state C equals to encoder embeddings, then encoder state equals to state H, state C, sampler equals to TFA dot sequence to sequence sampler dot training sampler, decoder cell, that's LSTM cell, and a dense layer, and a basic decoder. Is there a model, direct model you can call, or that's typically how people construct the encoder decoder?
Yeah, that's typically how encoder decoder.
Okay. Okay.
Yeah.
And this probably can be written a little better in terms of, you know, the style. But let's look at D2L and see how D2L implements encoder decoder. Let me just encoder decoder architecture. Okay, so let's look at that. If there is something better.
Yeah, but with respect to seek to seek models that we are looking at, I don't think so. It might be a better way to put together the architecture because this,
Yeah,
uh,
yeah, I think so. I think there's gotta be a better implementation. I remember TensorFlow had something near machine translation and attention. Um, but I guess this involves attention. So okay, so this involves attention, but we don't have a basic structure of encoder decoder. Seems like data preprocess.
there is a notebook with respect to the TensorFlow neural machine translation with attention that we looked at last time.
Mm-hmm.
There
Yeah,
they have implemented it. I think so.
yeah,
You
with
might be referring
attention.
to
Yeah,
yeah
with
that
attention.
attention.
Yeah, and I was just looking for something without attention, and to see if there's a encoder decoder implementation with classes, separating encoder and decoder basically, um, and using language data sets obviously. So anyway,
Yeah, here.
let's yeah, go ahead.
Mhm. I also had a query with respect to sampled softmax technique that is introduced, that is written in the third point with
Mm-hmm.
respect to. So I had a query with how this computes the approximation based on the logits only, because they say there are two techniques to do that. And yeah, this is
Mm-hmm. What was your question?
how does this help tf.nn dot sample softmax loss with respect to the computing the probabilities uh, of uh, this data set. So with respect to the original large vector, uh, and how is it computationally optimized?
Yeah,
So
that's
instead of having 50,000 classes, you just keep say 10 classes, and one of these 10 would be your actual output. So you just compute a loss over these 10. So one would be the actual class, and 9 of them would be randomly picked classes or randomly picked words. So it's much less computationally intensive compared to doing a softmax on 50,000, right?
mm-hmm. Mm-hmm.
Hmm. Yeah, yeah, I get that now. So how are they uh, broken down from 50,000 to vectors to those particular number of
So it
10 or uh,
so you just reduce the number of classes, right? That's all. One of these classes has
okay.
to be your actual target. That's all, and the rest of them are random. But on
Mhm.
inference, you don't know what your
So,
actual target is. So in inference, you always have the whole 50,000.
hmm. So I think so the training sampler helps here too with respect to uh, having those embedded classes to uh, some sort of distribution, which we can then later on sample from. The decoder that uses the training sampler here.
I didn't get that.
So the training sampler, I think so, helps in this with respect to uh, mm, uh, making sure the distribution is well within the range, or to make that distribution, this training sampler helps. Because
Yeah, it is
in the
used
end,
here.
yeah,
But what distribution are you talking about?
so we that's what I was confused about, this training sampler. What does its function is with respect to then uh, taking the distributions? Yeah.
Yeah, I have the same question. So Mayank, you think that this training sampler is involved in the sampled softmax technique?
Yes. Yes.
I see.
Yeah, I think it's the same thing. Sample. Okay. Benchen, can you just Google that training sampler?
Sure. And it's part of the TensorFlow add-on. Seems like it's not even in the TensorFlow main module. A sampler for use during training. Only reads inputs, return argmax of the RNN output logits. So returns the position of the biggest logit of the RNN outputs.
And it would seem like this place is where the input should be reversed, if any. But I don't see it. I'm looking at the code for training sampler, and I don't see. I'm looking at the source code for the training sampler. I don't see anywhere where the input is reversed.
I think the sampler is used in the decoder, right? It's one of the arguments in the basic decoder. So it should be doing what the
It's used
sampling
in default.
softmax thing. Yeah, it should be the one doing that.
It's only reversed for encoder.
Yeah.
Okay. Cool.
Okay. Let's proceed forward to bidirectional RNNs. He did not explaining in great details. Basically, it's quite intuitive. For machine learning translation or machine translation models, you actually want to see the words after the word that you're trying to predict or encode, and so that you can get a context, right? So however, in time series tasks, you don't want your model to see what's afterwards. So to implement that, people came up with bidirectional recurrent layer to be able to kind of flow forward and backwards, and it will the bidirectional layer is basically called it like this. So you, and then you passing the carousel.layers.gru into that bidirectional function, and then it will just create a clone of a GRU layer, but in the reverse direction, and will run both and concatenate their outputs. So even though a GRU layer has 10 units, now the bidirectional layer will output 20 values, or 20 will have 20 units per time step. Okay.
So this should be a better than reversing the string. You can just go with bidirectional RNNs.
Yeah, I would say, like, I think a lot of later implementations are just bidirectional RNN, right? I mean, that's
Yep.
what I saw.
Yep, I think so. In BERT too, it's bidirectional.
Yeah, the only reason not to
So-
use bidirectional is if you have to forecast something and you're not allowed to
Right.
look ahead.
Yeah. So I think you're right, Gotham. The reverse of the inputs doesn't matter anymore when you have
Yeah.
bidirectional RNN. Okay, so this is pretty straightforward, and again, the code is straightforward as well. It's just additional passing your layer, GRU layer, into an additional layer of bidirectional in Keras. Now, so I wonder what's the order of this? How is the reverse RNN? When is that executed?
They happen independently, right? So they can happen at the same time, parallelly. They don't depend on.
Okay.
And then you just concatenate whatever output you get.
Right. Yeah. Okay. I didn't know that. Cool. All right. Beam search. I think basically the idea behind beam search is that you want to be able to search within your top most likely or promising sentences, and choosing the top ones, or the most promising one to be your actual prediction in the end. So you're really stacking a search optimization algorithm on top of your machine learning output. And I think sometimes we need to be data scientists need to be more open-minded and look beyond machine learning algorithms. A lot of times optimization algorithms are really helpful, and it could be search, it could be routing, it could be something else, or sorting, and there are a bunch of algorithms that we could look into to further process or post-process your machine learning outputs. And I think this is the idea of it. So, I think what's important here is your encoder decoder model is greedily outputting the most likely word at every step. And it might end up with a suboptimal translation. So, and he give an example of that, right? So if your second word is wrong, and it becomes will, and the third word is going to have the best word at that time step, but it will say you, but the fourth word will become play. So in the end, you might end up with a suboptimal translation. So in the end, that's where beam search comes in, and it keeps track of short lists of the k most promising sentences, and at each door step, at each decoder step, it tries to extend them by one word, keeping only the k most likely sentences. The parameter k is called the beam width.
I have a question.
Yeah.
I just have something to add. So what it looks like is beam search is used only during inference. It's not part of the
Correct. Yes.
training, right?
Yeah. Exactly.
Okay.
So it's not part of the training. Yeah, it said inference. So let me just try to see if I can draw this. So basically, if you have how, and it's 75% probability, and it outputs, let's say, 3 words. Your model is predicting that, and this could be well, and I'm just following his example, right? How well and R do, and that's 36% probability, and that's 32, and that's 16. However, at first level, your model had 3 most probable outputs, how, what, and that's, so this is 75%, this 3%. Oops. And you have U, and that's 1%. So basically, then you also have, a bunch of words here with different probabilities. What you want to have is, you want to have 3 models now, and you want to times the conditional probabilities. So in this case, for the first model, you will have 75%, 0.75 times 0.36 times some other words, basically down there. And so I guess the computation is really scaling up pretty quickly. But you want the highest score of this with a conditional probability, multiplying each other up. In the end, you're choosing the most probable sentence, or most couple k probable sentences. And that's what it is. So to prevent, prevent a scenario of suboptimal translation. So in the end, you can choose even, what's the most probable, or what makes most sense, actually. So any questions on this? Okay, and in the code, he actually had beam width of 10. So instead of 3 words, and instead of 3 models, we could have 10. And yeah, so you're searching literally through 10 scenarios instead of 3 to find the most likely scenario, most perfect, reasonable translation. And one of the use cases of this is, you can also search not just through translation, but also through another use case. One of my friends is a joke expert. He writes monologues late night monologues, and he uses he develops his own AI model to write jokes. And so after a language generation model, he told me he was using Beam search to find the best jokes that the model outputs. That was also very fascinating. So. And as he said, unfortunately, this model would be really bad at translating long sentences. Once again, the problem comes from limited short-term memory of RNNs. Even with LSTM and or GRUs, attention mechanisms are the game-changing innovation that addresses this problem. So, okay, any questions up to this point? Did I lose anyone?
Nope.
Okay.
Nope.
All right. Attention mechanisms. This was initially introduced in 2014. When I first got into this, I thought transformer was the first attention, but well, little did I know it was already introduced in 2014, and there are different ways of calculating attention as well. And I think transformer wasn't even, I think even a scale dot, even the dot product attention was not actually invented in the transformer paper. I think the only thing that they invented was self-attention, multi-head self-attention. That was the invention. But it used a bunch of other techniques that were introduced earlier than the transformer paper in 2017. So just a little quick background. However, I think attention, just like the word, right? It has its own intuition, and I just want to kind of talk a little bit about that. I thought this was quite good from D2L. And let me just read this. Attention is a scarce resource. At the time you're reading this book and ignoring the rest, thus similar to money, your attention is being paid with an opportunity cost. To ensure that your investment of attention right now is worthwhile, we have been highly motivated to pay our attention carefully to produce a nice book. Attention is the keystone in the arch of life and holds the key to any work's exceptionalism. Since economics studies the allocation of scarce resources, we're in the era of attention economy, where human attention is treated as a limited, valuable, and scarce commodity that can be exchanged. Numerous business models have been developed to capitalize on it. On music or video streaming services, we either pay attention to their ads or pay money to hide them. For growth in the world of online games, we either pay attention to participate in battles, which attract new gamers, or pay money to instantly become powerful. Nothing comes for free. All in all, information in our environment is not scarce, but attention is. So I think that's something very important to kind of have that intuitive understanding of why attention actually works. And just like CNN and trying to mimic our visual cortex, right? And how we actually read images. I think attention is trying, the attention mechanism is trying to do the same thing in terms of how we actually pay attention to certain things in life. So when inspecting a visual scene, our optic nerve receives information at the order of 10 to the power of 8 bits per second, far exceeding what our brain can fully process. Fortunately, our ancestors had learned from experience that not all sensory inputs are created equal. the capability of directing attention to only a fraction of information of interest has enabled our brain to allocate resources more smartly to survive, to grow, to socialize, and such. And just like what explained in terms of the intuition, we're trying to do the same thing with the attention model. Basically, through the process of translating "I drink milk," at each time step, we want to know which outputs or which parts of the encoder parts that the outputs should pay attention to, right? And just like what I was trying to explain at the beginning of the session, even in medical space now, they're trying to use RNN with attention to use attention to explain, hey, what event sequence actually caused the actual disease or illness to happen. And in the paper that Mash shared at the beginning of the session, it was heart failure. What event sequence or what sequence of diagnosis codes actually led to the eventual outcome or of heart failure. So, and same thing with language or NLP tasks, right? So instead of event sequences, it'll be sequence of words. Okay, so I don't think he put in any codes into the notebook. So I'm gonna actually walk through a little bit on the codes from D2L, because I think it's actually important to talk a little bit about the codes and also different attention scoring functions matching the text here. I think he talked about two ways of calculating attention scores. However, he didn't go into great details of these, but perhaps we can talk about that here. So one is additive attention, and I think that's what was introduced here, and it was developed by Badano. I don't know if I'm pronouncing his name correctly, but perhaps it's Dimitri Badano. And he originally developed this groundbreaking technology or technique with attention and RNN together. And the way how additive attention is done is basically, well, if you look at encoder and decoder structure, what's added here is the attention layer or alignment model. And he kind of explained it a little bit here, but he didn't go into much detail. However, the way how it's calculated is here, the additive attention scoring function. And you have the query vectors and the key vectors, and you have the query weights and key weights, and you have the the value weights right here. And so these weights are all trainable, obviously. And you have the 10-inch function here. And then the query and key are concatenated and fed into MLP with a single hidden layer of hidden units is H, a hyperparameter. And this is the code. And it matches here, right? So in the end, these are actually the key vectors. That's the query vector. And it's passing to a MLP multi-layer perceptron, and that's what it is. That's what this is. and you have the implementation here. So any questions up to this point? Okay, so I think this is one implementation of attention and attention scoring function, and there's another one that's called scale.product attention, and that's what's used in the transformer, and I think it's also talked about here, and I believe it's a variation of what's talked about here by Min Than Luan, and he developed the dot product attention or multiplicative attention. And a variation of that is scale dot product attention. And again, it also deals with query key vector, which we'll probably talk about more in the next session. And the way how you calculate the attention weights is transpose of Q times K divided by the square root of dimension. And this is dot product. And again, this is passed to here, right? And softmax stats times the value. So that's another way of scoring the attention weights. So there are two ways, major ways of calculating the attention scoring functions. Okay. And attention is also used in the context of image caption, right? So basically with this image, where do you want to actually pay attention to generate a bunch of text describing the image? So you could have a CNN, right? And outputting some feature maps, then using a decoder RNN equipped with attention mechanism to generate the caption. So that's also a brilliant use case for combining image task and language task together. And a lot of times explainability is huge. I think it's cool to get the accuracy or the error to be less, but a lot of times in real worlds, we want our models to be able to explain what actually drove the model to decide which outcome it has. And that's why I think a lot of times there's a lot of creative ways to engineer or design your classification models in terms of picking which label you want, the labeling strategy. Maybe you want a certain outcome and you just label that and let your model to be able to explain what actually determined that outcome. That's a pretty widely used technique or design pattern in real world. So,
if I may expand just a little bit, this part on explainability that Jaron points us to is LIME, and I'm sure many of you have seen LIME and Shapley in your own anything you've done where you've had to do a little bit of interpretability and explainability. And this paper that he refers to is the original Lime paper from Carlos Guestrin and Marco Tulio Ribeiro, and so on. And yeah.
Cool. And also, if to kind of expand on that, if you think about feature importance is the 2D way of explaining a model, then attention is perhaps the 3D way. Adding an additional dimension of sequence or time steps. And because a lot of times if you look at basically, let's see if I can draw this. I mean, if you think about a tabular data, right, data sets, and each row, let's say, is one patient, patient 1, patient 2, patient 3, patient 4. And we have a column of heart failure, HF. And this is 0, 1, you know, whether this person had heart failure or not. Now I can totally do a random forest model on this, right? So, and explaining, you know, which feature led to the heart failure, right? So feature number 8 all the way to feature number Z. Okay, so I could do that, and using that as feature, you know, to using this to be able to extract the features that are important. However, I could also do if I have the sequence data, then just one patient, right? I could have time steps, right? So this is the first diagnosis. And this is, I don't know, July 1st. In August. I have the second diagnosis. And I can go on and on for every single patient, right? 3 patients, 4 patients, 4th patient, and to like thousands of patients or tens of thousands of patients as long as I have records for them. Now, this, I'm adding one more dimension on top of what I had here, right? And this is where you can use attention to be able to tell, hey, you know, what sequence or what sequence of diagnosis codes actually led to the heart failure. But in this case, it will be, hey, you know, maybe August 1st, or, you know, on this date, I have a heart failure. So, and previously, no. So no, but all of a sudden I have heart failure here. And same thing with second patient. It could be like, you know, during one particular time, and this person had a heart failure. So all of a sudden you went from a 2D label set to 3D with one extra dimension of time. And this is what I meant by attention being able to explain feature importance with time sequence. I hope that was clear enough. So, and I think this is pretty promising. it can be used even outside of, it doesn't have to be just, language task. It could be, again, medical health space, it could be some other spaces, industries as well. So any questions up to this point? And perhaps we can dig a little more into the code and the mathematics, either within next session or after the next session. I don't know how Gotham wants to plan this, but
I have a question about this last diagram.
which one?
Where they have the encoder feeding into the decoder, as well as the output of the decoder coming into the itself.
This one?
Yeah, there's a more detailed diagram of this a little bit later on.
That's in the transformer?
Oh yeah. Did we get up to there? No.
No, we did,
Okay.
we did not. This
Okay.
will, yeah, this will come later on, because yeah, we did not read this, and this is a newer architecture from 2017.
Okay, no
And,
problem. I'll ask the question later on.
yeah, no worries. And again, I think they actually invented a multi-head self-attention, not attention itself. And so I just want to clear that in terms of the background or history of attention. So any other questions? I know I went a little quick on some of the attention architectures because of the time, but I do hope we have more time to dig into the code of attention, different attention architectures later on.
If we want to have a look at the interpretability, there's a great digital post which I've shared the link to.
Cool.
It has some awesome visualizations with respect to the attention modules that we have discussed.
Yeah.
If you guys go through it, yeah, that kind of visual perspective also helps to uh, have a intuitive understanding and of why the things work uh, the way it does. So that's my 2 cents.
Great. Thank you, Mayank. We'd love to take a look at that. Let's look at, is that augmented RNNs? Yeah. Okay. Attention and augmented recurrent neural networks. Great. I know this still has pretty good visualization and pretty good articles. But it definitely, they usually have pretty long articles, so it takes some time to read through them.
Plus
Great.
the visualizations with respect to the cursors. So if you move your mouse, yeah, that also helps to visualize how those uh, vectors or tensors in that space affect the context of that summed up attention group, as we might call it. And how does that differs, and what are the connections?
Yeah, and Jay Alamar has pretty good visualization as well, but I believe yes. So I would encourage everyone to read this as well. I read through this. This was quite good. Mechanics of sequence-to-sequence models with attention. and how attention helps you helps the model to interpret the model.
Yeah.
Yeah. So let me post this. He always has really good visualization for different architectures. Okay. Anyone else? Oh, I just clicked. Anyone else has any thoughts before we wrap it up? 3:11. And as you can see, right, each word, context, decoder, I am student, right? Each time step. That's a very helpful visualization. Anyone else? Okay. On that note, I guess I want to thank everyone for joining the session. I really appreciate it. And next time we'll talk about Transformer. It will either be Gotham or me. But thank you.
Thank you very much.
Thank you.
Thank you all.
Thank you.
Thanks. Everyone, take care. Bye.
Fantastic job, Wensheng.
Thank you, Mesh.